In 7.6, we do integration using tables. And so before we even get started, I want you guys to check out the table of integrals document that I posted there just above this video and just kind of take a look through it. And I'll give you a moment to open that up, and then I'll kind of talk about it as well before we get into this first example. The word tables, the way the word table is used here is pretty old-fashioned. It might be edging even on archaic. By tables, they really mean a big list of formulas, and we still use that term. So the table of integrals, if you have a physical copy of the textbook, these will be in the reference pages at the end of the book. But from what I understand, if you have the ebook, it does not include the table of integrals. I don't know why. This a big part of learning integrals is learning to do them from this huge list of formulas. Anyway, I've posted it, so if you've got in your book or not, it might just be easier to reference this PDF. Anyway, and so, okay, as you look at that and you notice at the top there, the beginning of the first page, it's just talking about the basic forms, and so there it lists several of known antiderivatives. Everything here is going to be an indefinite integral, by the way. So it lists a bunch of known integrals that we know, and you might even notice numbers 11 through 15. Excuse me, let me say 12 through 15. Those are the antiderivatives of tangent, cotangent, secant, and cosecant. So before I had referenced in another lecture video the integral of secant u du, number 14, and there you go, and there you see the rest of them as well. So that's nice. By the way, when you take your first exam, you are going to be able to use this huge document for the table of integrals. Now you're only going to be able to use it on questions that pertain to it, but it will be at your disposal. Okay, let's kind of scroll down and look at some of the other ones. So you notice they break these up into the different forms. So a little bit further, you see forms involving square root a squared plus u squared, where a is greater than 0. And you see a bunch of different formulas involving square root a squared plus u squared. And you get to the next page, and now it's forms involving square root a squared minus u squared. There's a reason why they use the variable u. There's going to be quite a bit of u substitution going on here, and so for that reason, they don't use x, they use a u, because we recognize these are just general forms of integrals, and so oftentimes you need a u substitution to make it fit one of these formulas exactly. Okay, and then a little further down, square root forms involving square root u squared minus a squared. Okay, and after that, we're all the way up to number 47 now, forms involving a plus bu. Okay, those go for a while, and then we get trigonometric forms. So different powers of sine, cosine, tangent, cotangent, right? And lots of other things. Okay, quite a bit of those. Inverse trig forms. Okay, so those are, integrals of inverse trig. All right. And then we've got exponential logarithmic forms and hyperbolic forms, forms involving square root 2au minus u squared. Tops it off, and you see it goes all the way to there's 120 different formulas, all categorized. Okay. Very nice. Now, one question kind of arises, where do you think these formulas come from? All of these are derived from those 5 techniques, right? U substitution, integration by parts, trig integrals, trig sub, and partial fraction decomposition. I mean, those are it. Those are the techniques. So every one of these formulas, somebody applied one of those or maybe a combination of those techniques. And so now we have this big list. Okay. Let's do this first example here, finally, that you see in this video. Integrate using a table of integrals. So you'll know that you're allowed to use the table of integrals, say on a test or a quiz, if I say specifically in the directions that you can. And if it does not say that, then you got to do it the long way. All right, so part A, let's integrate x squared over 3 plus 2x quantity squared dx. Okay, so as we look at that, we think, all right, if I'm going to use a table of integrals, first thing I need to do is identify which form this takes, and then from there I can sort of piece out the specifics. And so it's kind of nice we went through the form. So, obviously there's no square root here, so it's not going to be square root a squared plus u squared. And if I keep scrolling down, I went all the way back to the beginning and I started scrolling again. Okay, it's not going to be the next one. That is a square root. It's not going to be square root u squared minus a squared. Is this a form involving a plus bu? And yes, definitely, because I see that 3 plus 2x. Okay, so take a moment and kind of scroll through that page, forms involving a plus bu, and see if you can identify which of those will fit here. Okay, so scrolling down, it's just a matter of time. This one lines up pretty well. This is about as easy as they get. It's going to be number 53, formula 53. And it lines up very naturally. The u in the formula for us is just the x, right? The a is 3 and the b is 2. And so we can see that all pretty easily. So really it's just a matter of filling in our answer because we can see what that equals and we know our values. So sounds pretty good to me. So following number 53 and being careful we're copying what we should, we'll have 1 over 2 to the third, big parentheses 3 plus 2x minus 3 squared over 3 plus 2x minus 2 times 3 times the natural log of the absolute value 3 plus 2x, parentheses plus c. Again, just filling in the u as x, the a as 3, and the b as 2. And from there, we probably want to simplify things if we can. We don't have to go too crazy. I think this works. Let's just keep that 1/8 on the outside. We don't need to distribute that. It's perfectly fine here. And then 3 plus 2x. Let's make 3 squared a 9. 2 times 3 is 6. And I think that'll be it. There's our answer right there. I kind of like, just simplify the simple things, right? Like 2 to the third or 3 squared or 2 times 3. And that actually, to be honest, helps me in the grading because it's clear which formula you used and did you do it correctly, if this is all the simplification that you have. Okay, very nice. I think we have time for another one. Let's take a look. Well, looks like I wrote the first line. That's okay. Let's pretend. Oh, bump the table. Let's pretend we've got integral 6x squared over 3 plus 2x quantity squared dx. So all I did, if we compare these, what happens if we just throw a 6 out in front there? And I've kind of given it away already. Well, something like that, we can, of course, just pull the 6 out front, and then we've got the same thing we had. So don't be fooled by any constant multiples. We'll use formula 53. Again, I won't go through listing all those details. So what would we have? We would say, okay, if there's a 6 in front, then we would multiply a 6 out in front of that answer. And you might even write that, as 3/4 in front if there's a 6 times this whole thing, if we got that integral there. I think we have time for even another one because that didn't take too long. This one will be a bit more challenging. Let's see. Integral of x squared over square root 5 minus 4x squared. Okay, this will be a good one. Okay, well, is this a form a plus bu? You know, b can be negative, but we've got an x squared there, and so this is not going to be a form a plus bu. Okay. It's going to be one of those square root forms. Let's see. If I go back to the beginning and start scrolling down, is this square root a squared plus u squared? We'll probably say no, because we are subtracting, right? 5 minus 4x squared. Is it the next one, square root a squared minus u squared? And yep, I think that's it. We're subtracting, and the constant comes first. Okay, so it's somewhere between number 30 and number 38. Can we identify which of those it will be? And it appears to me to be number 34. Okay, so what does that mean for the different pieces of our formula? Well, here there's just a u and an a. And now this one, the difficulty is increased a little bit, so we're going to have to be careful. Write the u, if we were to match up our integral with formula number 34, that's definitely the one we need to use based on the denominator. But let's be really careful. Okay, so a will equal the square root of 5. All right, because a squared gives us 5. And the u is going to have to equal 2x. Now this is interesting, right? So in the formula, we see u squared here and here. But we need this part of it to match. We need to pick u to be 2x. And then we're going to have to end up making an adjustment for how the numerator fits. Okay. So what we're basing the a and the u on has got to be the form, right? And that's the denominator here. So we got a to be square root of 5, u to be 2x. Now, how does this make things more difficult, right? If u is not just equal to x, if u equals 2x, there's a u substitution going on. So a couple of things we need to consider. For one, I'll just show you all this. We need to consider du, right? We can't simply replace dx with du, right? It's not going to work that way. If u equals 2x, then du equals 2dx, and now this is, you know, a u substitution that we're familiar with. We can divide that on the other side. Dx will become 1/2 du. Very easy to just go right past that and just jump right into the answer. But no, slow down. There's a u substitution going on here. Okay, also, we're going to have to replace the numerator with u's. Okay, so it's easy to think, well, you know, in the formula, I've got u squared, here I've got x squared. Okay, but it's all got to, you know, all the puzzle pieces have to fit, and it all has to be consistent. So if we're taking u to be 2x, then we need to think of x as equaling u over 2. So this u equals it has that dual purpose. So we can get the du from it, and we can also solve for x. So this u over 2 is going to go in for that numerator. And let's continue this on the next page. And I'll try and fit as much as I can because it's kind of all relevant so far. When we substitute, here's what we will have. Okay, so that x became u over 2 squared. Our square root, I'm just going to keep that as 5 and recognize the a. All right, so 5 minus, and then the 4x squared, of course, is u squared, and the dx became 1/2 du. So now if we clean this up, and pull the constant out front, right? So we'd square that half, pull out the 1/4. We'll also pull out this 1/2, give us 1/8 out there. And then we'd be left with u squared in the numerator and square root 5 minus u squared in the denominator. And now it looks exactly like the formula. So there was some, you might say, massaging of our original integral to get it to match that formula number 34. We can, maybe it's not too hard to identify it's that formula, but it takes a little work to get it to fit perfectly. And, you know, just right, this constant 1/8 comes out. And so we needed that for every little piece of the puzzle to click together and for it to all be consistent with our choice of u equals 2x and all that. And also, you know, kind of note here, now I'll go back to this. We had to take u equals 2x, right? So you might say, well, could I just take u equals x and then kind of rearrange this one? Well, no, the algebra just doesn't work that way because it's inside the square root. You know, that's not going to be possible. Or if it is possible, it's going to certainly be a lot more difficult than what we've got going on here. Okay, so pick your u to be the, you know, kind of match the form, if you will. And much easier to work with things not in a square root. Okay, I think I've made the point. Okay, now our integral looks exactly like 34. So I'm just gonna, you know, write out that formula there with the u's in it. So we've got a 1/8, and then here's what that integral equals, right? Big bracket, since the 1/8, negative u over 2, square root, the a squared, I'm just gonna fill in the 5, minus u squared, plus, that's a squared over 2, right? So 5 over 2, inverse sine u over, and now there's an a, so that's just square root 5 plus c. Okay. And then to finish off the problem, let's plug in our u's, and we'll have it. So we know that u equals 2x. So I can plug in 2x right there. That would be 4x squared, and there's another 2x here. And you can see I've gone ahead and circled this one. And so that answer would get full credit. You could argue there's some, you know, kind of relatively simple things we could simplify, right? Like 2 over 2. And, you know, maybe you could argue, it wouldn't be too bad to distribute the 1/8. So I went ahead and did that version as well, right? So negative x over 8 and 5 over 16. You could certainly answer this way. That's not too bad at all. But, you know, just make the point, don't feel like you have to really go for the simplification necessarily to get all the points here. Either one of those would be full credit. And again, like, where did that formula come from, right? You know, here to here. Let's look at this one. Which of the trig, not which of the trig, I might have given it away. Which of the integration techniques would you use to end up with this as your formula? And, well, I believe that's going to be a trig substitution, right? We've got the square root. Now, 5 is not a perfect square, but we could work with that. So you'd set up your triangle, and it makes sense that maybe inverse sine could come out of this, you know. So we can kind of see that. Okay, let's stop this video here. See you in the next one.